To determine the electron pair geometry and molecular shape of SnCl2, begin by drawing a Lewis diagram. Refer to the periodic table of elements to find the number of valence electrons for each atom. This molecule has a total of 18 electrons, 4 electrons from tin and 7 electrons from each chlorine atom. After drawing the Lewis diagram, count the number of valence electrons in the molecule. Compare this value to the calculated number of valence electrons to confirm the correct diagram was drawn. Given that there are 3 electron groups around the central atom in this molecule, the electron pair geometry is trigonal planar. Since there is a lone pair present on tin, the molecular geometry is bent. This lone pair exerts slightly more repulsion on the electron groups, resulting in a bond angle less than 120 degrees. This is a ball and stick model of SnCl2. The electron pair geometry is trigonal planar and the molecular shape is bent. Although the lone pair on tin is not shown in this model, it is very important because it influences the molecular shape by decreasing the bond angle between the chlorine atoms from 120 degrees to 95 degrees. Now, let's figure out which types of bonds are present in this molecule. Refer to the periodic table to find the electronegativity values of each atom. Tin has an electronegativity of 2.0 and chlorine 3.0. Since chlorine has a larger electronegativity value, it will have a greater attraction to the electrons when compared to tin. This is shown by chlorine having a partial negative and tin having a partial positive. Finding the electronegativity difference between chlorine and tin will assist in determining which types of bonds are present. When referring back to the possible bond types, this molecule has polar covalent bonds. Although there are polar bonds present, the polarity of this molecule cannot be assumed as polar. To predict molecular polarity, begin by drawing dipole moments for each bond. Dipole moments show the direction of the greatest electron density. Start the arrow at the positive end and draw the point of the arrow towards the negative end of the bond. To determine if this molecule has a net dipole, add the vectors together. Begin by drawing the first vector, paying attention to the length and the orientation. Then, continue by drawing the second vector, starting from the head of the previous vector. Continue to draw vectors until all are used. If the head of the final vector is located at the tail of the first, then no net dipole moment exists, and the molecule is considered nonpolar. Seeing that the dipole moments do not cancel, SnCl2 has a net molecular dipole moment and is considered polar.